Hello, lovely humans! Jen Foxbot here. We are continuing our Math Mondays deep dive into machine learning by looking at a new approach to different types of machine learning algorithms called logistic regression. So we looked at gradient descent, which is a wonderful approach to solving machine learning problems with data that can be mapped to a polynomial function or something that is wiggly and wavy. But sometimes we have different types of needs. Sometimes our data doesn't fit to a polynomial function. It's more binary, yes, no, or toad, frog, cat, dog, that type of thing. And in that case, we can call these types of problems classification problems, where the output must be a specific value. It's also sometimes called discrete. So it's a cat, a dog, a horse, etc., but nothing in between, not continuous. It's discrete. So those types of problems don't work very well with gradient descent, especially for linear gradient descent, because let's look at an example. So let's say we are trying to figure out how many toads are in our environment and how many frogs are in our ecosystem. So we make some measurements and we make a plot. Toad is on the vertical axis and frog is on the horizontal axis. And so we'll just say that our measurements of frog fall down here. We measure 3 frogs, and then we go out and we find 2 toads and maybe another frog and maybe another couple of toads. So if we were to use our gradient descent linear approach, or even linear regression approach, we might get something like this. And then we would take a photo of one of the creatures that we find, and we would put it into our machine learning algorithm, and it would probably give us something here. And we'd be like, what is that? Is that a trog? Is that a frode? Merging the toad and frog, it's funny. Language is funny. So this is a little bit nonsensical. It's fun, but nonsensical. Maybe that's what you want from your machine learning algorithm. That's totally fine. There's some cool, funky artwork that people have been doing with it. But if you legitimately are trying to classify the types of creatures in your ecosystem, maybe you want to better understand biodiversity. Not exactly helpful for your scientific cause or your curiosity cause. So this is where classification comes into play. So with classification, we only have specific values. And you know me by now, I hope. Or if you're here for the first time, welcome! I like to start simple and work up to more complex examples. And so we are going to start with binary classification, where we have something that can only have 2 options. So a classic binary example is 0 or 1, on or off, up or down, nothing in between. So in this case, for our classification problem, we are going to have data where it can only be 0 or 1. That's it. Cool. Okay. So the approach to this mathematical kind of representation is to use logistic regression. And we will see why when we are like, what does the hypothesis function look like for this? Because previously with gradient descent, our hypothesis function, h of x, which is our guess, the machine learning's guess for the prediction of new data, it equals like theta 0 x plus theta 1. That would be the linear example, and then you just add more parameters and more x terms if you want higher order polynomials. That form for the hypothesis function isn't going to work. That's continuous. We could have a fraud in there. We don't want that, at least not for our purposes. So we're going to use a different equation. And our hypothesis function is going to look like this. We have h theta of x. We're going to use the same notation for our hypothesis function. But in this case, it is going to equal g, we'll define g in a second, of theta t times x, where you have many different parameters. This is going to be a matrix, times our input data x, with g of some variable. We're going to use z as our stand-in variable for now, equals 1 over 1 plus e to the negative z. So this is called the sigmoid function, or the logistic function. Hey, logistic regression, what's up? And so when we plug in our function g, then we get, this is our variable that we are inputting into our function g. Our hypothesis function is then going to equal 1 over 1 plus e to the negative theta t times x. Boom! That's our hypothesis function. So what does this actually look like? I like pictures as well. So if we were to plot this, actually, hold on, I'm gonna fix that. We're still gonna use blue, but we're working on a different scale here. So if we plot that, we have x down here, and we have h theta of x here. So if this is 1, then our sigmoid function maps like this. Oops, hold on, I messed it up. Okay, hold on. I kind of messed that up. Okay, hold on. We're gonna try that again. One more time, bear with me. It's hard to draw sometimes. Okay. I'm overthinking this. Okay, so I was trying really hard to have this function cross the horizontal axis at 0.5 or 1/2. It's not exactly to scale, but bear with me. So that, okay, that's a little better actually. Okay, so I apologize that this is not as pretty as I would have liked, but you work with what you got sometimes. The key also here is that there are asymptotes at 0 and 1. And so the output of the sigmoid function is always between 0 and 1. You can modify it so it crosses the vertical axis at a different spot. But it is always, as it is written here, it is always going to be between 0 and 1. And so a key thing to note is that as x goes towards positive infinity, our hypothesis function goes towards 1. And in the other direction, as x goes towards negative infinity, our hypothesis function goes towards 0. Look at that! We have a function that allows us to map values between 0 and 1. So now our hypothesis function must be between those two ends, those two numbers. And so the key now is then to fit your parameters to your training set, and then you plug that in to the sigmoid function. So the last thing that I want to note, in the next video we'll go into more detail of logistic regression, but the last thing that I want to note is, how do we interpret this? Like, what is our machine learning algorithm going to spit out if we give it some new data set? Well, we are going to give it a new data set based on X. It's going to have, let's say it's a new picture of a creature that we discover in our environment, and we're like, what do you think, algorithm? Is this a toad or a frog? And so we are going to get out h of x. Let's say we get out a 0.7. We're going to get a number between 0 and 1. What does this actually mean? It means that it's a 70% probability that it is a toad. And we say toad because we identified toad as equaling 1 and frog is equaling 0, and that's how we trained our algorithm. You could just as easily flip those, but you want to be consistent, and that's the key here. So that this is a 70% probability that your data set is going to have that label. And whatever that label means is going to depend on your data set. So another way to look at this is that H, our hypothesis function, is a probability where P stands for probability. And one of the possibilities is that y equals 1 for a given x and parameterized by theta. And I also want to note that the sum of all of the probabilities, so in this case we only have two possible outcomes, y equals 0 or y equals 1. So if you add these up, then you have to get 1 because the creature has to be something. Assuming that you took a picture of an amphibious creature that's either a toad or a frog, it has to be either a toad or a frog. Can't be a horse. At least not yet. Okay. So yes, let me know if you have any questions on the sigmoid function or on why we would use or need classification problems. And in the next video, we are going into more details on logistic regression, specifically the decision boundary. Yay! Don't worry if you're like, what is that? That's why we do these videos, because we learn more things. Yes. Okay. Thank you very much for watching, friends. If you enjoyed this video, please share it with your friends. Consider subscribing because then it helps me know that I should keep doing these. All right. And feel free to ask for different topics too, because at some point we're going to finish up with machine learning. All right. Thank you. We'll see you soon. Bye.